Hi everyone, my name is Wanchao Liang and I'm an engineer from the Pytorch core team working on distributed training. Today, we're going to talk about Pytorch and large language models. Pytorch has been playing a critical role in the AI evolution and the entire life cycle of large language models. Researchers and engineers could quickly prototype transformer models, build efficient tools from model pre-training, post-training to fine-tuning and inference using Pytorch. The open source community has built a wide range of tools using Pytorch to push the boundaries of large language model capabilities. Open source innovation that is happening across the world contributed significantly to the AI evolutions. At Meta, we greatly value open source and believe that open innovation could lead the AI models be safer, more secure, and efficient. To further enable the ongoing research of transformers in the era of large language models, the Pytorch team also started many efforts to help accelerate the AI evolutions and enrich the open source ecosystem. Starting from large-scale training, the Pytorch team has been building many training algorithms through improvements to Pytorch, for example, n-dimensional parallelisms. To make fine-tuning a pre-trained model more accessible, we have implemented memory-efficient training techniques and fine-tuning techniques through new open libraries like TorchTune. We have also built out muscles to deploy models on different devices via Execute Torch, run efficient inference via GPT-Fast, making large language models be openly accessible everywhere. We'll walk through each of them in today's talk. Next, let's talk more about large-scale training with Pytorch. The industry invested heavily into large language model pre-training. What is special about pre-training and why it requires foundational investments? Today, pre-training imposes lots of technical challenges. First, model size grow exponentially over the past few years. Today, many large language models ranging from 7 billion parameters to more than trillions of parameters. Second, huge amount of data needed. Data size also increasing crazily where trillions of tokens are needed in order to get great model quality. Given the large model size and huge amount of data, the training would take millions of GPU hours or hundreds of years to finish. So we need a robust large-scale training system that could scale the model training to tens of thousands of GPUs, staying training efficient and converging as if we are training in a single device. This requires many innovations, from hardware level to software level and many system level optimizations. Within a robust large-scale training system, distributed training becomes critically important. The Pytorch distributed library offers a wide range of tools to build such a system. We have Torch Run for launching distributed training jobs in cluster. We offer communication primitives where user could call collectives like allReduce, allGather using beacons like Nico. Parallelism primitives. We built out dtensor to express tensor-level sharding and device mesh to express multidimensional communicators in the context of n-dimensional parallelism. These primitives together enable the system developers to build efficient training solutions that could scale their model training for different use cases. On top of these primitives, Pytorch Distributed also offers end-to-end parallelism solutions, including our popular data parallel solutions, distributed data parallel, fully sharded data parallel, and the model parallel solutions, including tensor parallel, pipeline parallel, to further scale model training to thousands of GPUs. For instance, we have been collaborating closely with Databricks and IBM team on parallelism solutions. Our solutions empower Databricks to scale the mixture of experts training to 3,000 GPUs using hybrid sharded data parallel and dtensor. For production training, Pytorch Distributed offers an efficient checkpoint save and load solution to support long-time training with fast failure recovery. Our collaboration with the IBM research team yield over 10 times improvement for model checkpointing time. Apart from distributed algorithms, there are many other important training techniques that could further scale and improve the training efficiencies. To name a few that Pytorch provides: activation recomputation, a technique that could save the memory during forward by recomputing activations again in the backward. Mixed precision training recipes, where it allows training with lower precision D types and keep convergence. This could not only save the GPU memory, but also improve the training efficiency. Torch compile. We introduced a compiler stack for Pytorch models since Pytorch 2.0. Torch compile could improve training performance without changing the model code. It provides the capability to fuse computation operations and perform communication optimizations. All of these techniques could further improve the training performance. So you may wonder that there are so many training algorithms and techniques needed for efficient pre-training. How could developers actually use them all together? To demonstrate end-to-end training with those techniques, we're introducing Torch Titan. Torch Titan is an open source proof of concept for large-scale training with native Pytorch. Torch Titan is built with Pytorch design principles, focusing on simplicity and ease of use. It implemented three-dimensional parallelism training for transformer models, including fully sharded data parallel, tensor or sequence parallel, and pipeline parallel. It showcased how to compose many efficient training techniques together in a simple manner, allowing extensibility across software components and achieve great performance. For example, users could easily configure their selective activation recomputation policy for memory saving. Turn on Torch compile to enable compute fusion. For H100 and above GPUs, users could enable IPA training to improve the T-flops. Furthermore, the checkpoints saved in Torch Titan can be easily converted and loaded into TorchTune to start fine-tuning with custom data size. Now, wrapping up large-scale training, we're expecting model size and number of GPUs continue to grow. There are so many exciting challenges ahead of us that we're working on right now. To name a few: fault tolerance and fast restart. This become critical as node failures become very common at large scale. Preserving debuggability across our software stack is essential for failure root cause. We also want to continue improve training efficiency while keeping power constraint in mind. As we are heading towards multimodality large language models as the first-class citizen, we need to tackle new challenges that may be different from text-only large language models. We still want to preserve the interoperability into fine-tuning and inference. Solving these challenges are both exciting and critical for the future. Next, I'll hand it off to my colleague Ivan, who will talk about fine-tuning for large language models. Thank you.
Thanks, Wanchao. Hi, my name is Evan Smothers. I'm an engineer on the Pytorch domains team, focusing on fine-tuning. I'm going to talk about fine-tuning large language models using Pytorch. We can think of the different stages in the lifecycle of large language models as a funnel. The large-scale training discussed by Wanchao sits at the top of the funnel. It requires the most memory, the most compute, and as a result, it's generally the least accessible. At the bottom of the funnel lies on-device inference. Here we run distilled or quantized models locally with minimal memory footprint. These models are broadly accessible, since anyone with a smartphone can use them. They also tend to be tailored to specific applications. Fine-tuning sits in the middle of the funnel. It's the means by which we bridge the gap between large pre-trained models and efficient on-device inference. While LLMs are pre-trained on massive corpora of data, there are actually a lot of tasks that they're not especially good at. One very common example would be math problems, where pre-trained generalist LLMs perform notoriously poorly. One goal of fine-tuning is to turn generalist models into specialist models. This is often informed by whatever the task of interest is. For example, maybe you work in a radiology lab, and you want a model to summarize radiology reports. This is an example of both domain and task adaptation, the domain being the medical domain, and the task being summarization. A common response to, my model is not good enough at task X, is to use a bigger model. As we'll see in the next portion of this talk, This is not always an option. If we're going to deploy our models on device, we need them to be lean. This is really the essence of fine-tuning. Given a task and a desired memory profile, what datasets, modeling methods, and training techniques can we use to maximize our model's performance on the task, subject to said memory constraints? LLMs are often pre-trained on whatever the latest state-of-the-art hardware is. But many fine-tuners, such as those in the popular subreddit r/localllama, only have access to a couple of older generation GPUs. We can do some quick math here. Most open source LLMs fall somewhere in the range of 1 billion to 100 billion parameters. If we store all of our weights in half precision like bfloat 16, that's 2 bytes per parameter. If every parameter is trainable, that's another 2 bytes per parameter for gradients. If we use an optimizer requiring momentum like Atom, that's another 4 bytes per parameter. Adding that all up, even a smaller model like Llama 2 7B would require 56 gigabytes of memory, putting it out of range of many consumer-grade GPUs. This is not even considering larger models like Llama 3 70B, where the parameters alone will require multiple 80 gig GPUs just to store them. On the other end of the spectrum, many people rely on Colab for free-tier GPUs. These have 16 gigabytes of VRAM and no bfloat 16 support. In that case, even just storing all of the Llama 3 8B weights in half precision will cause an These very different hardware profiles necessitate a range of different techniques for memory efficiency. The objective of supervised fine-tuning is basically the same as free training. It still uses next token prediction. One of the biggest changes is around the scale of the dataset. This means that it's relatively cheap to launch a bunch of concurrent fine-tuning experiments. And so, ease of experimentation and ability to get quick feedback on model performance become really important for fine-tuning workflows. Common paths for getting these signals include evaluation on academic or custom benchmarks for model quality, or more qualitative evaluation via text generation. Once a model is fine-tuned, it's also common to quantize it to further reduce the memory footprint. We'll see more on this in a bit. Finally, there are a lot of solutions out there across fine-tuning, evaluation, quantization, generation. It's not always easy to convert a fine-tuned checkpoint from framework X into one that can be quantized by library Y. More importantly, there are often many layers of abstraction wrapping the actual training code. Researchers and practitioners alike often want to tinker with the particulars of the training loop. It's not always easy to do that in the existing solutions. To address some of these challenges, we've released TorchTune, a library for easy and transparent fine-tuning of large language models using pure PyTorch. TorchTune onboards the latest and greatest techniques from both PyTorch and the broader ecosystem to make fine-tuning more accessible across a range of different hardware setups. TorchTune provides simple and hackable training recipes that can be copied and modified right from the command line. We give users direct and transparent access to the training code. This makes it easy to try out new techniques. We've had new recipes like quantization-aware training or multiple alignment methods onboarded to our library just by modifying our existing recipes. Our core library consists of modular building blocks that can be easily swapped out for quick experimentation. We provide model builders for easy one-liner access to canonical implementations of state-of-the-art models. Say you want to onboard some new attention technique. You just need to write the class, build it in one of our existing models, or write your own, point the training recipe to it from the command line, and you're off. We provide interoperability with the broader ecosystem via integrations with Hugging Face, Weights and Biases, Eleuther's evaluation harness, and more. We partner closely with the open source community and have received community contributions onboarding DPO and PPO training scripts, Gemma, Qwen2 models, and more. Our checkpoints can also be exported for inference with Executorch. TorchTune leverages tools and techniques from the broader PyTorch ecosystem to increase the accessibility of fine-tuning. We support low-precision techniques like full bfloat 16 training or reduced precision optimizers. All the standard memory-saving techniques like CPU offload, activation recomputation, or gradient accumulation are supported directly via the canonical PyTorch APIs. Other, more specialized techniques like fusing optimizer step and backward or sample packing are also available and we demonstrate them transparently in our single-file training scripts. One of the most common ways to improve memory efficiency is via parameter-efficient fine-tuning, where the majority of model weights are frozen and smaller trainable adapters are inserted to save gradient and optimizer memory. We provide simple training scripts for LoRa and QLoRa, and we leverage the latest Pytorch distributed APIs to support fine-tuning of Llama 3 70B on two 4090s via QLoRa and Torch Compile. Finally, we provide details of peak memory and tokens per second on different hardware setups for all of our training scripts directly on our README. Looking forward, there are a lot of things to be excited about in the fine-tuning space. Language models are becoming increasingly multimodal, with an ability to intersperse image, video, or audio data as context for the language model. This will make memory efficiency even more critical for fine-tuning. It will challenge fine-tuners to find new ways to apply adapters or shard their models for distributed training. Multimodal signals don't have to be restricted to only inputs. With agent-based LLM workflows, we can even call image generation models as part of our inference flow. These are just a couple examples of some exciting techniques around multimodality that are on the horizon. Next, I'll hand it off to Kimish to talk more about what we can do with our fine-tuned models, some of the big technical challenges there.
Thanks, Evan. Hello, my name is Kimish Patel, and I'm a software engineer in Pytorch Edge team at Meta. Today, we will be talking about enabling on-device inference of LLMs. So far, we talked about leveraging large-scale distributed infrastructure to train LLMs and subsequently using smaller setup with single-node GPU to fine-tune pre-trained model for a specific use case. In continuation of that, in this part of the talk, we will talk about deploying such a fine-tuned model on a constrained device for inference. A fine-tuned model can be deployed across many surfaces, such as server-side inference that provide LLM inference as a service, or local inference, where the model or service is run locally on device, which may include laptop or desktop with local GPU, smartphone, AR/VR devices, or embedded devices. Given the large-scale nature of LLMs, one may naturally ask, why are we even doing local inference? Well, local inference provides users to trade off capability of a very large general model against task-specific, relatively smaller model that can be deployed locally for privacy, latency, cost, and other reasons such as available data bandwidth through carriers or internet providers, which may vary significantly across different geographies. However, enabling large-scale models across these surfaces have significant challenges, since these models require significant amount of memory and compute resources, and we have limited amount of those on our target for deployment. For example, on high-end laptop or desktop, you may have tens of gigabytes of RAM, while even high-end phones may have somewhere between 6 or 12 gigabytes of RAM. These get further accentuated when we go to wearables, which may have 1 to maybe 2 gigabytes of RAM. Available power due to lack of active cooling also varies significantly across the spectrum. Furthermore, modern SoCs contain wide variety of task-specific accelerators such as GPUs, neural engine, image processing blocks, etc. These constraints throw some challenges for deployment. For example, limited on-device memory means we must reduce the model size. Not only that, if we have different use cases such as message summarization or smart compose, each such use case cannot ship its own large model due to limited memory and disk space. Furthermore, we must make sure these models run efficiently to meet the latency requirement, which in turn means we must figure out how to leverage the available hardware to the maximum. Let's take a look at how we can address each of these challenges. Techniques such as quantization and sparsity help reduce model size. Quantization enables us to compress information into fewer bits by leveraging redundancy. However, many of the large models are dense in information despite being large in size. This has resulted in more innovation in the field of quantization, where new algorithms like HQQ, GPTQ, SpinQuant has enabled low-bit quantization. Pruning and sparsity is another technique that relies on neuron density, meaning leveraging those parameters that are more important than the others and pruning the other ones with relatively less information. While quantization and pruning help reduce model size, it may not be sufficient if we have to deploy entirely separate model for every on-device use case, such as message summarization or smart compose. Low-rank adapters allow us to deploy one model with different adapters for different use cases, and thus still allowing us to leverage single foundational model. Furthermore, we must run these models efficiently to meet latency requirement. These models are heavy both on memory bandwidth, meaning how much memory do I need to read to run one iteration of inference, and on compute, meaning how many operations do I need to do to run one iteration of inference. And each deployment surface has a limited amount of those. We have to ensure that we are able to leverage these resources maximally using efficient kernels for matrix multiplication, attention, which are the workhorse of these models. Okay, so we talked about the solutions we can employ to address these challenges. Let's see how Pytorch enables these solutions. Torch.io is a Pytorch library where we are working with community to enable low-bit D types such as int4 or FP6 and quantization schemes such as GPTQ, HQQ, as well as providing pruning APIs. Using these APIs, you can quantize a large model to 4-bit or 3-bit D types. TorchTune, that was introduced earlier, allows us to fine-tune small-size adapters. And for executing models efficiently, Pytorch ecosystem provides two solutions. Torch Compile, which generates efficient code for backends such as GPUs and CPUs by doing, among other things, aggressive fusion to reduce memory bandwidth requirement. On the other hand, ExecuTorch, which is a very lightweight runtime with first-class support for leveraging on-chip accelerator, like Apple's Neural Engine via its delegate interface, is well suited for deployment across phones or embedded devices. Both Torch Compile and Execute leverage native graph capturing technology, export. Exported graph can be shape specialized or can support dynamic shape via symbolic shapes. Such graph then form the basis for the rest of the stack. In the case of Torch Compile, it can be inductor plus Triton. Inductor Triton backend provides lowering for various ops in Triton language, which gets compiled into Kuben. On executor side, once the graph is captured, entire graph or parts of the graph can be relegated to specialized backends. For example, to leverage Apple's Neural Engine, we can use Core ML or MPS delegate of ExecuTorch to lower parts of the graph to be executed on the Neural Engine. Alright, so today we talked about the challenges involved in extremely large-scale training, efficient fine-tuning, and then performant inference for large language models, whose size range from hundreds of billions of parameters to a few billion parameters. But our story doesn't end here. This is just the beginning of generative AI's capabilities as we add more modalities besides stacks to models' learning capacity. Such modalities include vision, speech. You can imagine the growth in complexity across our stack to support these modalities. Meta is well positioned to take on these challenges to leverage generative AI capabilities across its products, including family of apps and reality lab devices. And we are committed to do this in an open ecosystem. These are exciting times both for the use cases that AI will spawn and the challenges we will have to tackle to enable them. Thank you.